In this video, we're going to give an overview of what we have learned so far about titrations. The reasons why we're using titrations to learn about acid-base character is because it gives a graphical understanding of what happens when you mix an acid with a base. Notice that that's what we've been doing so far. The idea of how to calculate the pH when you mix acid and a base of different concentrations, different volumes, that's exactly what a titration curve is giving you. So let's start just giving the overall shape. We will typically draw pH regardless of if we're titrating an acid or a base. The y-axis is the pH, and if we are titrating the strong acid, it means that the strong acid is what's in the Erlenmeyer and the base is what we're adding slowly on through with a burette. If it's a strong base, say, let me give you an example. If we are titrating a strong base 0.1 molar HCl with, say that you're titrating 20 milliliters, and you're titrating it with a strong base such as sodium hydroxide 0.1 molar, the first pH will be, because this is a strong base, this will be 1. The titration will proceed kind of slowly, and there's a difference with a weak acid, until it jumps the pH. A much sharp jump than weak acids. So strong acids will have a much sharp jump, and the equivalence point is when you have added as many moles of base than acid there was at the beginning. In this case, because the concentrations are the same, this will happen at the same volume. Okay, and the pH is 7, and the pH here will tend towards 13 in this case, because this is 0.1 molar. The pH of a 0.1 molar base, strong base, is 13. Notice that if the initial concentration were 10 to the minus 2, for example, you would start at 2. So this would be, and I'm going to put it as dot, if you have 0.01 molar HCl, provided that you are titrating it with 0.01 molar sodium hydroxide, it would take the same volume. Okay, but the starting point would be different. However, the equivalence point will be the same. And of course, then it would tend to go to pH 12. All right. So what does this tell us? We are capable of calculating the pH at any point given any amount of acid and base. This means we are now capable of solving problems such as what is the final pH when you mix 20 milliliters of HCl 0.1 molar with, I don't know, 5 milliliters of NaOH 0.1 molar. What is the pH when you mix this up? Well, notice that to do that is exactly the same as calculating the pH at this point. Okay, so any of these problems of mixtures that are not presented as a titration can be understood as a titration. Okay, the same can be said when we are titrating a strong base. And again, even though we are titrating a strong base, the pH is what it's plotted. It's not the pOH. We plot the pH and say that strong base is lithium hydroxide, 0.1 molar. Okay, and we are titrating it with, to be a little different, nitric acid, and I'm gonna say 0.05 molar. Okay, so half, and I have 10 milliliters of this base. What shape is this gonna be? Well, initially 0.1 molar, the pH is 13, so I'll have something like that, and then a sharp jump all the way here. The equivalence point, it's still at 7, and notice that the acid is a half of concentration of the acid, so sorry, of the base, so we will take twice as much volume, so this will be the equivalence point. Okay, strong acids and strong bases titrations are fairly straightforward. It should not take a lot of calculations. It's something different when we are studying weak acids or weak bases. First of all, so if I'm plotting the titration of a weak acid, say that I have 1 molar, right, it's fairly concentrated, of a weak acid, say of acetic acid, with sodium hydroxide. Let's say that I have 10 milliliters and sodium hydroxide 0.5 molar. Okay. First of all, even though it's 1 molar, you take the negative log of 1, that's 0. The pH of a 1 molar solution of acetic acid is not 0. You need to calculate with the ice table. Okay, and you'll see a titration curve of this shape. The equivalence point is the same as just calculating how many moles of base it takes to neutralize the initial moles of acid. But so this will be, if it's 10 milliliters, this is twice as much. This will be at 20 milliliters. Okay, and so first of all, this point is calculated using the ice table, using the Ka. Okay, halfway of this point by 10 milliliters, this will give me the pKa, which for acetic acid I think it's around 4.5. Okay, and what I have in the equivalence point is this should be above 7. Just making sure it's above 7, because what I have as a result of the equivalence point is a base. So to calculate the pH of a solution with a base, I need to use the ice table using the Kb. Okay, and this is the pH, and then this point will be going towards the concentration, the pH, which should be around 13.3, something like that. Okay. All right. Now, sometimes there is the confusion as for, oh wait, so if I'm titrating a weak base, say that I'm titrating, say, ammonia. Ammonia has a Kb around 10 to the negative 5, which is a pKb of 5, which therefore the conjugate of the conjugate acid has a pKa of 9. Again, if I'm titrating pH versus volume of acid, in this case, let's say HCl, alright, say that we are titrating a 0.1 molar solution of ammonia, say 10 milliliters, with 10 milliliters of HCl, 0.1 molar. The equivalence point will take place at 10 milliliters of acid. The initial point will be something like that, and then whoop. Okay, so the equivalence point, at this point you will have, this is 7. So initially you just have ammonia. How do you calculate the pH of ammonia? Well, using the ice table for Kb. Halfway of the titration curve, you have at 5 milliliters, you have a 50-50 solution of ammonia and ammonium ion. So based on the Henderson-Hasselbalch equation, you can still, so concentration of base over concentration of acid, when these two are the same, this is 1, logarithm of 1 is 0, pH equals to pKa. So careful here, pKa in this case was 9. Careful here, even though we are titrating a base, halfway of the titration, this will give you the pKa, because that's what it's giving us. As long as we're titrating pH, this will give us the pKa. We could see that if we were using pOH in the y-axis, that in the middle point of the buffer area would be giving us the pKb. Okay, and in this case, what you have left is just the acid, so you need to calculate the pH at this point with an ice table using the Ka. Alright, hopefully this video gives some perspective. There's some repetition here, but it's important that you get the idea that now you can calculate the pH of any solution that contains more than one acid or base in solution. Okay, and that's what we will practice more explicitly, but we believe that the graphical representations are very, using the word graphical, they're very graphical to picture graphically where we are in terms of mixing acids and bases.